Hello everyone, I am Manish Agrawal and thanks for watching Edupedia World videos. For the next few sessions of states of matter, we'll study gas laws starting with Boyle's law today. So what are gas laws? They are basically laws or rules governing the behavior of gases. Okay, so they will help us to analyze how gas changes its behavior or changes its nature under different conditions of thermodynamics, that is under different conditions of pressure, volume and temperature. Okay, so if I change pressure, what will be the effect on volume or temperature, or if I change volume, what will be the effect on pressure and temperature, or say if I change amount of gas, say number of moles, then what will be the effect on pressure and volume, and so on and so forth. Alright, so gas laws are basically empirical laws. Do remember that all of the laws which we'll study here are empirical laws. There is no such proof as such for them. They have been observed by various scientists, and based on that these laws were discovered and propounded. Also, these laws that we will study are applicable only for ideal gases, not on real gases. Okay, in fact, one of the definition of ideal gas is any gas which follows the gas laws which we are about to study in the next few sessions. Okay, so they will help us to determine variation of thermodynamic variables like I already explained, and basically using all the gas laws we'll study 4 gas laws. Okay, over here, so using all the four gas laws, we derive at a complete equation defining the behavior of ideal gas. Okay, this equation is also called equation of state and or ideal gas equation, and you must have already seen it before, and even if you haven't, it looks something like this. PV is equal to nRT, where P is pressure, V is volume, N is number of moles of molecules, okay, of a gas, of an ideal gas. T is temperature in Kelvin, obviously always in Kelvin. R is called universal gas constant. Okay, you can say it's like a constant of proportionality, and let's assume that it has some value which we are not concerned with right now. So basically all the gas laws combine to form this equation, PV is equal to nRT. Alright, but we are studying it in the reverse order. We are assuming that this equation is true. Okay, this equation we have memorized and we are well aware of all the variables which are present in this equation, and now using this equation we will try and understand the gas laws. Okay, so this is a better way to understand and derive various formulations for the gas laws. Okay, so just remember that PV is equal to nRT is the ideal gas equation. Now let's start with the Boyle's law. So Boyle's law determines the behavior of gas under constant temperature condition. So it takes first number of moles of the gas as constant, that is to say we are talking about a fixed amount of gas. Okay, which means that I have taken a container, a closed container, and this closed container I have put in some amount of gas, and now this amount of gas is not being changed. The container is not being opened again. Okay, so whatever number of moles N that is present will remain constant. Plus there is an additional condition for Boyle's law. Okay, this is the law or behavior of gas which Boyle derived, that he kept temperature to be constant. For all his analysis he made sure that temperature of the gas inside the container remains to be of the same value, say let's say 30 degrees centigrade. Okay, so it will always remain to be same. This means the only variables which are changing, thermodynamic variables, are pressure and volume. So Boyle's law is basically nothing but a relation between pressure and volume. So let's see how the behavior of gas is observed. Okay, so PV is equal to nRT. N and T are taken to be constant. R, as I already told you, is a constant. It is a universal constant. So this means effectively as per Boyle's law, PV becomes constant, okay, which we have seen from ideal gas equation. We derived from ideal gas equation that since temperature is constant, PV is equal to constant. Let's say that constant is K, okay, small k, some random alphabet. You can take it to be P, Q, R, Z, T, any random variable. So PV is constant, and we also know that this constant has the value of nRT. Okay, in other words, I can say that pressure is, let's say for now, equal to K by V, or I can say pressure is inversely proportional to volume, or pressure is directly proportional to 1 by V. Okay, so this is what Boyle's law represents. Okay, that pressure and volume are inversely related. So if I have gas in this container, okay, this white bordered container, then if I increase the volume, okay, that is I shift the walls of this container further apart, so I'm increasing the volume of the container, then automatically the pressure exerted by gaseous molecules inside this container will decrease. Alright, similarly, if you change the pressure, that is now the walls are movable, okay, and if I decide to push the walls, alright, that is I'm decreasing the volume, then pressure will automatically increase. Or if I increase the pressure, then walls will automatically, okay, walls will automatically come close together, that is volume will decrease. Pressure and volume are inversely related. Okay, so that is one way of looking at Boyle's law. Other way is, since PV is equal to constant, okay, let's say the initial value of pressure was P1 and initial volume was V1. Now if I am changing the volume of my container to V2, then what is the pressure P? Okay, so this is a constant, I know that. Now volume has been changed to V2, then what is the pressure P2? Alright, so whatever its value is, I can say that P2 into V2 is also a constant, and it is the same constant nRT, okay, because this equation still holds. PV is equal to nRT. So P1 V1 is equal to K, P2 V2 is also equals to K. That means P1 V1 is equal to P2 V2. So this is another way of looking at Boyle's law. Okay, so both these boxes represent Boyle's law. Alright, and you must understand and remember both these relationships. Okay, they are just different ways of representing Boyle's law. Now two important things. One was obviously that n is constant, but the other more important aspect over here in Boyle's law is that temperature is constant. Okay, so such processes, okay, in which temperature is kept constant are called isothermal process. Okay, so this is a term again which you have to memorize, isothermal process. So what is the process? Process is we are changing pressure and volume, okay, but we are keeping temperature constant. So such any process in which temperature is kept constant is always called an isothermal process. Okay, so Boyle's law is nothing but a relationship showing the behavior of an ideal gas undergoing an isothermal process. So what is the graphical representation of Boyle's law? Okay. So we know that PV is equal to K and that P is equal to K by V. Let's say pressure is our y coordinate, that is we plot it on y-axis, and volume is being plotted on the x-axis. So it's something like y is equal to some constant C divided by x. So we have to draw graph for this particular equation. Okay, and what is this equation? This equation is basically like xy is equal to 1 or some constant. Okay, so it is an equation of hyperbola. Okay, now what is hyperbola? That is the that comes under the ambit of mathematics. We won't go into that, but we will look at how the graph looks. Okay, so this is how it will look. See why. P is equal to nRT by V, okay, or you can say K by V. So let's say my volume tends to 0. That means pressure tends to K by 0. Okay, if volume V it tends to 0, then P tends to K by 0. And what is 1 by 0? Okay, yeah, you can say it is not defined, or it is said to be very very high, that is it tends to infinity. Pressure tends to infinity. Okay, so as volume decreases, alright, or as it tends to 0, pressure tends to very very high values. Okay, but never actually intersecting the y-axis. Why? Because volume is never exactly going to be 0. Alright, that's not possible. And plus, if it is exactly 0, then 1 by 0 is not defined, so you cannot actually define pressure there. Okay, so that is when volume tends to 0. Now what if volume tends to very very high value, that is if V tends to infinity, then pressure is equal to K by V. Okay, which becomes that pressure tends to K by infinity. So this means, what is 1 by infinity? Infinity is a very very high value. Okay, so that means P tends to 0. 1 by very high value, P tends to very very low values. So as volume goes to very high values, pressure keeps on decreasing, but never actually intersecting with the x-axis. Okay, so this is the hyperbola. That is why the figure comes out to be like this. Okay, we know that it will start somewhere here and it will end somewhere here, and it is a smooth curve, so we simply connect these 2 points. Okay, and the nature of the curve, this is not the exact curve, but the nature of the curve is something like this. Alright, now what happens, okay, if this curve is tried to be changed? Okay, before that, once again remember that this curve has been plotted under isothermal condition. That means temperature is constant. So this curve represents a constant value of temperature, say T1. Alright, so such curves which represents a constant value of temperature are called isotherms. Alright, such graphs are called isotherms, and we have already seen that such processes are called isothermal process. So if I am trying to change the temperature, let's say I am increasing the temperature now. Okay, so first I studied the gas under temperature T1. Okay, now I want to study the graph, okay, or the behavior under a temperature T2, constant temperature T2, but T1 is less than T2. Okay, so the new graph is studied at a greater temperature. So once again, since the temperature is constant, the curve will look like a hyperbola. Okay, still we will have PV is equal to NR, but instead of T1 it will be T2. Okay, so PV is still constant. Alright, but will the curve be same? Will it be above this curve or will it be below this curve? That is the question. Okay, so how do we decide? Let's say we are talking about constant pressure. Okay, under both the temperatures T1 and T2, I keep a constant pressure. Say that constant pressure is P1. Alright, so that means if I look at volume of these two curves, okay, or if I look at volume of these 3 curves, let's say this is V2, this is V1, and this is V3, which has the highest value of volume? V3 has the highest volume and V2 has the least volume. Okay, so PV is equal to nRT2. P is constant, NR is constant. That means greater the temperature, greater will be volume. That means if T2 is greater than T1, then alright, then V2 will have to be greater than V1. Okay, so this means let's number them like this: V1, V2 and V3. Okay, so V2 will also be greater than V1. That means if I increase the temperature, curve shifts outward. Okay, curve shifts outward in this direction parallel to the previous hyperbola, and if I decrease the temperature, then curve will shift inwards. Okay, so here I can say T3 is going to be greater than T2 is going to be greater than T1. Each of these curve represent a particular isotherm. Okay, they all represent isothermal process. Another way of looking at Boyle's law, another curve, is by plotting P is equal to K by V, where I take y coordinate to be P and I take x coordinate to be 1 by V. Okay, so 1 by volume is taken to be the x coordinate. So it is a simple straight line, right? Y is equal to mx plus c, where c is 0, that is intercept is 0. So the line, straight line, passes through origin. Okay, so this is all simple mathematics, coordinate geometry, which you might have already studied, or if you haven't, you will study it later on in maths. And once you do that, this deriving the graphs using this equation will be very easy. Okay, you can even do it orally without writing them down. So this is how the graph will look if I plot on y-axis P and on x-axis 1 by V. Okay, in the initial graph on the x-axis we had volume. This time it is 1 divided by volume. Okay, 1 divided by volume. So the curves will be such that they all pass through origin, and once again each of this curve represents an isothermal process. That is, they have been plotted at constant temperature. So initially I kept my gas at temperature T1 and I observed its changes in pressure by changing 1 by volume, and this is the curve I got. Then I kept the temperature at T2 and this is the curve I got then at T3. Okay, so again, what is the relation between T3, T2, T1? So once again what you can do is, let's say, draw a perpendicular over here. Okay, so this perpendicular represents constant 1 by V. Alright, so P is equal to nRT into 1 by V. So 1 by V is kept constant for all these three curves. That means greater the pressure value, greater will be the temperature value. So which of these have greatest pressure value? P1, P2 and P3, right? So P3 has greatest pressure value, that means T3 will represent greatest temperature. That is why the relation is T3 greater than T2 greater than T1. Okay. So you must understand Boyle's law and also be able to plot both of these curves by yourself. Okay, so once you have done that, you have understood Boyle's law completely, and we can look at the usage of Boyle's law in form of numerical questions. Okay, so there are various use of Boyle's law. We just want to see its use, okay, from a numerical point of view. So let's take a numerical example. A gas is initially at 1 atm pressure. How much pressure needs to be applied to compress it to 1/3 of its volume? Okay, so you can read it on your own, but the concept behind it is that initially the pressure was 1 atmosphere, okay, and let's say volume was V1. The question tells us that we want to change its volume, we want to compress the gas to 1/3 of its initial volume. So the final volume should be 1/3 of initial volume. So V2 is equal to V1 by 3. So how much pressure do I need to apply? Okay, how much do I need to pressurize my gas in order to change its volume by such an amount? Okay, so it's simple. Boyle's law. Okay, they should have given that temperature has been kept constant in the question. Okay, don't worry, in your examination they always make sure to give such criteria. Okay, without that you cannot solve the question. So since temperature is constant, I can apply Boyle's law, which says that P1 V1 is equal to P2 V2, and P1 is equal to 1 atm, V1 is, let's say, V1, P2 we have to calculate how much pressure we needs to apply so that volume V2 becomes 1/3 of initial volume. Okay, so this gives you by simple calculation that P2 is equal to 3 atmosphere. Okay, or you need to apply, instead of 1 atmosphere, you need to apply a pressure of 3 atmosphere so that the volume is decreased to 1/3 of the initial value. Okay, so a very simple example, but this is all there is to Boyle's law. So until next time, and once again thanks for watching Edupedia World videos.